This is Shelley Physics. We're wrapping up our motion investigation with a conclusion by looking at our graphed data, and we're going to do something you've probably never done before. We're going to get an equation out of it. Now, if you felt some tinglies going up your spine at that moment when I said we're going to get an equation out of it, then you might have the physics bug. You might have to wait till after we're done with this, and you might feel a little bit of the tinglies, like anticipation, like, wow. Anyway, the rest of you think I'm nuts. I know, I am. So let's look at that constant motion graph. This is what your graph probably looks a lot like. Your numbers on the right-hand side in that little box are probably very similar, especially if you use the first data set. But if you look carefully at this, our data lines up exceedingly well with a line. The red dots are either just a little bit below or a little bit above or exactly right on that gray line that was plotted there as our line of best fit or linear fit. So this indicates a very good correlation. There's a number in that box, RMSE, that stands for root mean square error, the big word being the error. And it's very low. It's 0.01085. So it means our data points are very well lined up with the line. So we can trust this line. This is really agreeing with our data. And look at the form of that. It says y equals mx plus b. What is that? It's an equation of a line. So what I'm going to do is I'm going to pull this information out using that form. There's an m given, 0.6462. I'm going to write that down. And we'll see this paper in a second. 0.6462. The b value is a negative, oh, that's really low, 0.008208. All right, so switching over to that paper, our form of this equation is y equals mx plus b. All right, so you've probably seen that before, hopefully. You're in algebra-based physics, so you should have seen that equation of a line. But we have some actual real-life data from something that moved. And this data is telling us something, speaking to us about everything that moves in the same kind of way. So if we can create an equation from that data, then we can use that to apply to anything else in the world, in the universe, that moves like it. So first let's look at the y. What is on the y-axis? Switching back, the y-axis is position, and the x-axis, while we're at it, is time. So the y-coordinate is position, and we've got this slope. The slope of the line is the m. The x-axis is time, and the b, this is our y-intercept. I'll just write that generically in there, y-intercept of the equation. So that's what those characters are meaning. So in physics, position, that quantity, we're going to use x, because x marks the spot. Now position can also be y. If it's a vertical kind of motion, we would use y. If it's a horizontal kind of motion, like for the car in this case, we'd use x. If it's a radial kind of motion, like it goes out in any direction in a circle, we could use r. R, it's a pirate's favorite letter. And X always marks the spot on maps. Okay, it's a pirate's thing, you know. Anyway, getting back to it, we're going to use X to represent position, and time, we're going to use T. So, and I hope you're taking notes on this. Just write down what I'm writing. It's not going to be a lot of writing. Position, we're going to substitute then. So the y-axis is position. And it's kind of seeming a little funky here. I'm not switching the x and the y up here, but I'm saying that this x that we're going to put in now is an actual quantity. It's like m for mass, or what have we used before? V for voltage, I for current, R for electrical resistance, that type of thing. So x stands for position. So on the y-axis we've got position. Still haven't talked about the slope m yet, so I'll just leave that m. And on the x-axis, That's time. So we're going to use a t there instead. So if you take a look at it, we're transforming this generic equation of a line into something more useful that involves position and time. All right, at this point, let's look at this character here, b. If you look at it, negative 0.0082. What is that really close to? Let's glance back at the graph. Well, the y-intercept, that looks like 0. And it is very close to 0. And if you think about it, at 0 time, wasn't this object at a 0 position? So our y-intercept is about equal to 0. So we're going to rewrite this again, simplify it even more. X equals slope times time. So that's the last character we need to look at here, is that slope. What does that mean? Well, the slope of this line looks kind of normal for a line. It goes from 0 up to this amount, whatever that's up here. Now our graph is scaled a little bit, not perfectly like a square. If it were a square, then the 3 down here and the 3 up there would be of the same size, but you see it's kind of stretched up this way. So we can't really visually tell what kind of line this is. So let's go to the m. The m value is 0.6462. Now to get that, to arrive at that value, we need to take a rise of the graph divided by the run. Now, I guess to you it's going to be going like this, okay? So if we start at 0, 0 and rise up to a point on that line and then run over to where it is, then we're going to get the slope, and that's what that slope is coming from. So, but what kind of units is that? Well, on the rising slope, we've got feet. On the running slope, the time slope, we got, or the time axis, we got seconds. So to calculate this 0.6462 value, that's feet is the rise divided by seconds is the run. Feet per second. What is that? Feet per second is kind of like miles per hour. And we usually write mph, but it's miles divided by hours. And what is that? It's a speed, like a speed limit. So this m, this slope value, is a speed. But the other thing we can call it is a velocity. Okay, the slope is the speed or the velocity of the object. You might have noticed from the last lab we did, when you had 3 different objects, they had different slope values. Those slope values are the speeds of those objects. This speed of Lightning McQueen is a whopping 0.6462 feet per second. I'm sure to scale he was going really fast, but we're going to use, instead of m, we're going to use v for velocity. Now remember that the amount of velocity is also speed. So for constant motion, for constant speed objects, we have an equation of motion. So anything in the universe that moves with a constant speed, we can use x equals v times t. And if we just take that just one step further, dividing both sides by t, we would get v equals x divided by t. So however far something goes divided by the time it takes to go there is the velocity. Okay? All right. So that's one equation of motion that we extrapolated from this lab experience. Next, let's check out that acceleration graph. This one wasn't a straight line, it was a curve. Now if you weren't able to use graphical analysis from Vernier, thank you Vernier for providing that for free. If you weren't able to use graphical analysis and you had to do this by hand, you probably didn't come up with a quadratic equation or a slope or that type of thing for this, because it wasn't a line, it's a curve. So I'm going to pull this data down here also. It's a little bit more. We've got a y equals, and you can start writing that down. This is what I'm writing on paper. You see that under the quadratic? Y equals ax squared plus bx plus c. I'm going to write down the numbers that it gives us there. A is 0.5394. B is 0.4126, and C is negative 0.001245. Okay, so we have a quadratic now. All right, this is interesting. You could say that. That's a good bland descriptor. Okay, so this was our accelerating object. Let's keep that in mind. There's acceleration going on here. So this is the equation of motion we got out of an object that's accelerating. So let's again try to figure out what these pieces are. Well, like before, y is on the, let's see what's on the y-axis here. Position is on the y-axis and time is on the x-axis again. So y is the position. Remember, x is not the x-coordinate. It's here we're substituting y for x, where x is position of the object, equals a, instead of x-axis as a generic thing, we've got time on our x-axis. So I'm going to plug in a t squared there instead of x squared, plus b times t plus c. All right, so this is also a position function of time. But again, what are those letters that are in there? Let's go to c first again, this thing on the end. C has to be in units of position because there's nothing else multiplying it. So this is in units of feet, just like x is going to be in units of feet. So the c value up here is also very, very low, very close to 1. What does that mean? Well, it's actually also, just like the other one, a y-intercept. And it intercepts down here at 0. And that should completely make sense again. At time t equals 0, these two values would cancel out, and we're left with the position equals 0 at time equals 0. It hasn't gone anywhere yet. It's at the starting line. So this c is 0 again. It's approximately 0. So that's nice. It simplifies it a bit. At squared plus bt. All right. Now, what about t squared? Let's get past that for a second. Let's go to this term. The reason I want to go to this bt term is because it's similar. It's similar to m times t. Now it's a different letter here because with a quadratic formula like that, a, b, and c are just generic letters, whereas m would stand for the slope of a line. A curve doesn't have a single slope, so you can't really call b a slope. But if you look at m times t, where m is the velocity, that has the same form as b times t. So guess what b is? This would also be in units of feet per second. B is also a velocity. Okay? It has to have that same form. So we've got x equals at squared plus some kind of velocity times time. Now let's talk about that while we have it here. There's not just a single velocity for an object that's getting faster and faster and faster. That object is changing its velocity. It's speeding up or slowing down when it accelerates. So v is actually the starting or the initial velocity. Initial. I'm going to use that word over and over again. It means the starting velocity. V sub 0 means velocity in the beginning at time t equals 0. I might accidentally slip in a v naught on you. Naught means nothing. V nothing. V 0. That just means the initial velocity. And finally, on that word initial, if you've ever seen a computer program in the beginning when it starts up, it might say initializing. It means it's getting all the starting tidbits that it needs to get going. It's loading everything it needs to load. So this is the initial velocity times the time. And finally, we get down to this letter A. And appropriately enough, A is a good letter for that one. Because what is this object here doing? that this one is not. They're both moving. The constant speed one is moving with a constant speed. It does not get faster or slower. This one, the constant motion, is not accelerating, but the acceleration motion, the car going down the slope, is accelerating. So this graph shows acceleration where this one does not. So if we turn both those off, this term is the acceleration term. A has to do with the rate of acceleration. How quickly is the car speeding up or slowing down? For example, if the A value here, 0.5394, if I increase the slope, if I make it a steeper slope for Lightning McQueen going down that track, what would happen to that number? Do you think it would increase, decrease? It would definitely increase, because a steeper slope allows objects to roll faster down them or pick up speed more quickly. If it was a completely vertical slope, they'd be accelerating as quickly as possible as gravity can take them. So this number is something to do with the acceleration. In fact, it's half of the acceleration rate. And that's the one thing I can't really prove to you right now, but we will get into later in the course in just like a day or two, that this A is 1/2 the acceleration rate. Okay. Now this A right here is that one. I want to be specific there. This A though, so I said it's appropriate. This is acceleration. It stands for acceleration. So A is acceleration, V is velocity, X is position. And of course T is time. So just to sum this one up and write it in a format you'll more likely see, X equals initial velocity times time plus 1/2 acceleration times time squared. Now, in general, look at this creature. How is it similar to the constant speed equation? Do you see x equals vt for constant speed? Well, for the acceleration equation here, what's it start with? X equals vt. But it's not a single speed because that velocity isn't constant. So if we cover up this term, we get the constant speed equation, x equals vt. Why would I cover that up? Well, if an object is not accelerating, it's moving at a constant speed. It's not getting faster or slower. And if an object is not accelerating, that means its rate of acceleration is 0. So if this A value is 0, it's moving at a constant speed, and we end up with, ta-da, the constant speed equation. Okay, did you feel those tinglies up your spine yet? Do you realize what we just did? We just made an equation of something that moves in the universe, in the real life universe. I think that's pretty special. I hope you got a lot out of this. Thanks for watching.